In this video, we're going to be looking at logical identities in discrete math. So what are these logical identities? Logical identities are just going to be some rules that are going to help us simplify logical formulas. So when we simplify these logical formulas, it can help us find congruencies, so we don't have to rely on a truth table all the time. So let's start with the negation laws. So for the negation laws, it states this: if I have P or not P, then this must be congruent to true. And if I have P and not P, this must be congruent to false. So let's look at how this works. Let's say in this case P is true. Then not P must be false by the idea of a negation. So let's say P is true, so it'll be true or false. Remember, that's how or works. If it's true or false, then I'll always have true. So this is going to remain right. That's correct. Now, let's look at the idea of the second one here. It says P and not P. We're going to take the same definition here of P being true. If I have true and not true, which is going to be false, it's congruent to false, right? That's how and works. If I have true and false, then I'll have false. So that's how the negation laws work. So now let's look at the identity laws. So this is what the identity laws state. If I have P and true, then this is congruent to P. And if I have P or false, then this should be congruent to P. So let's look at an example in this case. Let's say we had P and Q, and we had and true. This would be congruent to P and Q. Let's say for the second one, we had same thing, P and Q, and we had or false. This would be congruent to P and Q. So this is what the identity laws are basically stating, right? If I have my original, which P and Q in this case represents P, right? And I have and true, this means that this will be congruent to whatever I have as P. In this case, my P is basically P and Q, right? And so for the second one, it works in the same way, but since it's or, we have false here. So if I have P and Q or false, it's congruent to just P and Q. So hopefully that made sense. Okay, so now let's look at the domination laws. So if I have P or true, it should be congruent to true. And if I have P and false, it should be congruent to false. So this is what the domination laws are saying. It's kind of similar if you think about it as negation laws, but it's different. So let's look at an example. Let's say in this case that my P is true. Then if I have, according to this one over here, if I have true or true, this is going to be congruent to true, and that's true, right? That makes sense. Let's say in this case, instead of P being true, it was false, right? If P is false, if I have false or true, it'll be congruent to true as well, right? And that's just how the or operator is working here, okay? Now let's look at the second one over here, and let's apply the same idea. If I have P is true, I have true and false, it's congruent to false, because that's how the and operator is working. And if I have P being false and false, I will have false. Okay, so hopefully that makes sense for domination laws. So let's look at the idempotent laws. So the idempotent laws state this: if I have P or P, it's congruent to P and P, which is congruent to P. So if I have true or true, it's congruent to true and true, which is congruent to true. And if I have false or false, it's congruent to false and false, which is congruent to false. So this is what I like to think about when I hear idempotent laws. Hopefully this makes sense. And let's move on to the next one. Okay, so let's look at the double negation. So if you're going to take the negation of not P, you're basically going to get P back again, right? So the idea of a double negation is if you take the negation of, let's say, another negation in this case, you're basically going to get the p-value back again, since we were using p here. If it was q, you'd get q back. Okay, now let's look at the commutativity laws. So if I have p and q, this is going to be congruent to q and p. So the order doesn't exactly matter. The commutativity law is basically telling us the order doesn't really matter. Order does not matter if it is arranged like this, right? If I have p and q, it's the same thing as saying q and p. And if I have p or q, it's congruent to q or p. Okay, so in this specific case, if we have or and aligned like this, then order does not matter. They're congruent to each other. Now let's look at associativity laws. So for associativity laws, let's say I had p and q, right, in brackets, and I had and r outside of these brackets, right? What if we could put this r inside and we could take the p out? We could do that. If the logical operator here is and on the outside and I have an and on the inside here, then I could potentially take out the p in this case and I can put the r in, right? This would also work for q as well, right? This would also work for q. So you're able to do that, and that's what associativity laws are all about. Remember, the logical operator here has to be the same. So if I have and there, I also have to have and here. Now this also works for or as well. So if or on the inside, then if I have or on the outside, you can still do the same thing. So that's how associativity laws work. Okay, so now let's look at the idea of distributivity. So let's say I have p and in brackets at q or r. This is basically congruent to p and q or p and r. The same goes for this one. So this is case 1, this is case 2. If I have p or in brackets q and r, is congruent to p or q and p or r. So what's happening here is kind of like foiling, and we're just taking this, so I'll just circle it. I'm taking this p and q, so there's going to be one term, and my next term is going to be p and r, it's going to be my next term. And in between them, it's just going to be this or that's between them here, right? Same thing goes here. We're kind of doing the same distribution, but we're going to have p or q, and between them we're going to have an and then we're going to have a p or r. Right? Hopefully that makes sense. We're just distributing it in how it makes sense logically, right? So you can see how it looks like when they're congruent when you distribute it properly. So now let's look at DeMorgan's law. So let's say we had a negation of p and q, which are in brackets. How can we do this? This is basically equal, or not equal, but I should say congruent to not p or not q. So what really happened here? How did an and go to an or? Now this is something really important that we have to understand about DeMorgan's law. You always have to flip the operator, right? So I'm going to always flip the operator. I'll put this right here. It's really essential, especially when you're taking this negation and you're distributing it in, always remember to flip the operator. So if I have an and, it flips to an or, right? So it goes from the negation of p and q to negation of p or negation of q, right? We can see it applies for or as well. So if I take the negation of p or q, it becomes a negation of p and the negation of q, right? So again, we're distributing this negation sign to p and q while we're also flipping our operator, right? It goes from and to or, and it goes from or to and, right? So that's how DeMorgan's law works. The next and final law we're going to be looking at is the absorption law. So let's say we had p and in brackets we had p or q. This is the same thing as p, or I should say congruent to p, right? And if I had p or p and q, right, then it is also congruent to p. Something that you can notice here is that the operator outside is and the operator inside is or. And here the operator outside is or, and the operator inside is and. So you can see that the operators have to be opposite. So pay attention, I guess, to the operators when you're doing absorption. So that's it for this video. I hope it helped. And in the next video, we're going to be looking at how we can use these logical identities to prove logical equivalences.